The boundedness property then, let f be continuous on the interval ab. Then we're going to prove this part 1, f is bounded on ab. So we've done the commentary and we've done the preliminary observation, haven't we? So let's just go down then and look at part 1. The preliminary observation was just focusing on the fact that if f is continuous at c, then f is bounded on an interval of this form for some delta greater than or. And also it said f is bound. The argument can easily be adapted to show that since f is right continuous at a, f is also bounded on an interval of the form a plus delta dashed for some delta dash greater than 0. And we looked at that in the previous vid. So here's proof of part 1 now then. Let's have a look at this. So let B be this set, all the x's in AB, such that f is bounded on a up to x. So it's going to start this set of B will be a set of this form. Yeah, a set of this form, because x belongs to these, and f is bounded on a segment. So this is what the set is then. Now we want to prove that the set B is equal to AB itself. So let's have a look at that then. First of all, is A the leftmost point in B? Well, A is in B, it says. So let's have a check. A would need to be in AB, which it is. That's fine. And is f bounded on A to A? Well, that's just a single point, and f of A is defined. So yes, it is. So A satisfies this condition and this condition. So A is in B, isn't it? So A is in B is fine. So B is non-empty. It's a non-empty set of real numbers. And secondly, B is bounded above by B. Well, we can see that by the way that the set is constructed, because basically all x's can be as in this set anyway. So naturally it would be bounded above by B, because this is the uppermost possible value in the first condition. So that's clear. So it's non-empty. It's bounded above by B, so by the completeness axiom, then B possesses a least upper bound. So this supremum of B, let C equals sub B, be this least upper bound. Now, all that is now required is to show that C, the supremum of this set, is equal to B, because if you show that this is supremum of B, then you know that this will extend all the way up, so we'll have A up to a value, and this supremum of this set. But basically, even though you find that B is the supremum of this set, that doesn't in itself prove that B is in B, does it? Because we've got a closed bracket here, because the supremum doesn't always need not necessarily belong to a set. So we actually need to show that sub B. Then when we get the supremum, we show it's equal to the value of B. We also need to show, of course, that B, the point itself, is actually in the set as well. Okay, so I think that's clear. So let's go down then and look at the reasoning on this section. So since f is right continuous at A, it's going to be bounded on this segment, isn't it, for some delta dashed greater than 0. So if that's the case, if it's bounded on this, certainly cut half of that positive value and close the bracket, and we see that f is bounded on this segment. So we can now say that C is greater than or equal to this, because this value is a segment on which f is bounded. So this value is in B, isn't it, capital B. So the supremum of B must be greater than or equal to this value, and this value itself is greater than A. Suppose by way of contradiction now that C is less than B, because we want to show that C, the supremum of the set B, is equal to B, don't we? So let's suppose for contradiction that C is less than B. C is greater than A then, because we just said that here. And f is continuous at C. It follows that f is bounded on this segment for some delta, isn't it? By the previous video. And we need to make delta sufficiently small around the point C so that it is suitable. From the definition of C, f is bounded on A then up to C minus delta, of course, because C is the supremum. So take a bit away from C, and that will be in the set B, won't it? So f is bounded on this set. And so if it's bounded on this set, and it's bounded on this segment also, then clearly because they join, it will be bounded on the entire segment A through to C plus delta, round bracket. So f is bounded on this, delta is positive, so cut that delta in half and put a square bracket, and we see that f is bounded on this segment. So C plus half delta is in B then, isn't it, by definition, because f is bounded on this set. So the C plus half delta must lie inside B, but this contradicts the fact that C is the supremum of B, because this is a bigger value than C and it's in B. So that contradicts the fact that C is the supremum of B. Therefore, our original assumption up here, supposed by way of contradiction that C is less than B, must be false. So we can only conclude then that C must equal B. So C is equal to B, and C of course is the supremum of B. So we've got the first part of what we wanted. All we now need to show is that B, the point itself, is actually in the set B and not just its supremum. Since f is left continuous at B, f is bounded on a segment for some delta star, isn't it? Like this, because it's left continuous, so that would be easy to show, just as we showed in the right continuous boundedness in the previous video. So f is bounded on this for some delta star greater than naught. Okay, and delta star, of course, necessarily is less than b minus a. So we're keeping it within the strip, so it's sufficiently small. B is equal to sub B, so f is bounded on any AD, where D is such that D lies between these two values. Now what does that mean then? Okay, let's start drawing a picture of this. So let's have a look what we're just putting together here. Here's A then. Here's B. Now f is left continuous at B. F is bounded on B minus delta star. So B minus delta star. This distance here is delta star then. Here's the set in question, and we just said that f is bounded on that set here. Okay, but B is sub B. Okay, so the supremum B, which is the value on which f is bounded. So f is bounded on any of these points where D is such that D can go right up to B. So D itself can go right up to B. So you could take it up to here. And you could say D can go up to B. So D could be all the way up to here. But it could go down to B minus delta star, which would be here. So you could choose any D in here, in this section. So necessarily then the value of D would be here. Okay, and so for such a D, f is bounded on this set, isn't it? So that set's alright. And now the way you've chosen D to be in here means that this set here, if you can see that, and this set here, the way D has been chosen are such that these overlap. F is bounded on this section, F is bounded here, so F must be bounded then. Here is, for such an A, F is also bounded on DB, and so F is bounded on the whole segment as we said. So B is in B. So there we go, we've pieced it together, we've explained what these intervals are in our mind's eye, and we can see there's an overlap when we look at these, and then we join them up. If it's bounded here, it's bounded on the whole segment. So F is bounded on AB as required. So this completes 1, and in the next section we'll look at part 2.